there at that time. Now he works in our Rudan University, and Professor Filipov emphasizes the tendency of Professor Skubachevsky to attract speakers from the whole world. The main point is that they are experts in differential equations, and that they are really high-level scientists.
Ну, я хочу настроить, может быть, на вечер, сейчас не буду долго говорить, надо приступать уже к более интересным математическим докладам, но вечером я бы хотел, может быть, вдобавок еще и как председатель ВАКа Российской Федерации, председатель Высшей аттестационной комиссии, обсудить, затронуть некоторые темы, связанные с подготовкой хорошей, качественной диссертации в области математики.
In the evening, Professor Filipov, who is also the chairman of Russian Higher Qualification Committee, wants to discuss problems of the preparation of high-quality dissertations.
Я хочу подчеркнуть, что на самом деле у нас здесь может получиться интересный разговор, потому что так получилось, что Математический институт имени Стеклова и МГУ делегировали право руководить экспертным советом в ВАКе по математике Университету Дружбы народов, а точнее профессору Скубачевскому.
This discussion is to be interesting because it occurred that Steklov Institute and Lomonosov Moscow State University offered the right to lead, to manage the expert council in mathematics of the highest qualification committee to the representative of Rudan, Professor Skubachevsky.
Знает, наверное, немножко даже Дмитрий Валерьевич Трещев слышал об этом, что поскольку 2 срока проработал председателем экспертного совета профессор Скубачевский, я неоднократно при формировании экспертного совета звонил Козлову Валерию Васильевичу и просил его: дайте кого-то из Стекловки председателем экспертного совета. Дмитрий Валерьевич знает, и мы с ним об этом говорили. И каждый раз они говорили: Владимир Михайлович, у вас в университете есть хорошие математики. Мы будем заниматься математикой, поэтому вот мы доверяем полностью РУДН, что вы назначите председателем экспертного совета по математике представителя РУДН, и как раз им 2 срока пробыл профессор Скубачевский.
Many times the chairman of the highest qualification committee asked Steklov Institute to present a candidate to be the chairman of the expert council in mathematics, and each time he received the response: there are great mathematicians in Rudan, please assign a mathematician from your university.
Ну, все-таки, Сергей Петрович, я бы хотел поставить, может быть, видение следующее. Сейчас есть очевидная тема, ведь в ВАКе у меня 44 экспертных советов. В целом, в среднем у них там около 40-50 человек. Это 2000 экспертов. В частности, по математике все диссертации в течение последних 8 лет проходили через профессора Скубачевского. И возникает целый ряд вопросов к диссертациям. В первую очередь, это вопросы актуальности и новизны результатов.
The question which is arisen is whether each mathematical dissertation is timely, and if all results in each dissertation are new.
Вопрос простой, понятно, когда вот у нас в Российской академии образования мы спрашиваем себя, а какие актуальные темы для диссертации по наукам в области образования, педагогики. И там должны быть какие-то актуальные темы, которые решают конкретные вопросы. Тоже понятно, когда есть актуальная тема или неактуальная тема, задача в технических науках.
For Professor Filipov, who is vice president of the Russian Education Academy, is quite clear what topics are timely in sciences about education and in sciences in engineering and industry.
А вот как быть в математике, когда есть раздел официальный в автореферате, первое, актуальность тематики, и как нам хотя бы порекомендовать, на каких принципах определять, она актуальная тема, или эта тема, я иногда критикую сам наших доцентов в университете, когда это была его диссертация 30 лет назад, и он по этой же диссертации дает тему кандидатской диссертации своим аспирантам 30 лет. А может быть, она и актуальна, эта математика. Вот как определить актуальность тематики в математике?
But the question about whether the topic in mathematics is timely or not is still open.
Ну и второй вопрос тоже простой. Я не буду затрагивать третий, четвертый вопрос, который связан там с внедрением для математиков, но вопрос новизны, он тоже в какой-то степени, понятно, что субъективный, но вот мы сейчас в ВАКе все равно разрабатываем понятие новизны в технических науках, какие решения технические, в педагогических науках, в медицинских науках. А сказать про такие науки, как математика или философия, что такое новизна или не новизна, вот есть ли какие-то общие подходы, кроме очевидного работающего механизма мнения экспертов, мнения ученых-экспертов?
Another open question is to decide whether the obtained results are sufficiently new or not. And this question is open not only for mathematics, it is open also for philosophy, for engineering sciences, and many other sciences. And at the moment, the only criterion is the opinion of experts, but we need other criteria as well.
Ну и, наконец, третью тему, может быть, обсудить сегодня тоже вечером. Это уровень математики сейчас, ну хотя бы не в школе, а в высшей школе. Сохраняем ли мы нужный, необходимый нам для такой страны, для таких великих математиков, как Сергей Петрович и другие показанные математики, сохраняем ли мы в преподавании достаточный уровень математики в наших университетах?
And one more question to be discussed this evening is whether the level of the mathematical teaching in our universities nowadays is sufficient to be descend our great mathematical history.
Я это хорошо понимал, потому что вырос в школе Сергея Михайловича Никольского, Льва Дмитриевича Кудрявцева, и обе диссертации защищал в математическом институте имени Стеклова, и был воспитан вот на таком хорошем, высоком уровне математики, который, как вы знаете, в России, в Советском Союзе в значительной степени курировал тогда Лев Дмитриевич Кудрявцев, который в течение 30 лет заведовал кафедрой высшей математики в физтехе.
Professor Filipov understands this very well because he grew in the famous school of academician Nikolsky, of academician Kudryavtsev. Both his dissertations are defended at the Steklov Institute, and he recalls that academician Kudryavtsev managed the mathematical chair at the Physical Technical Institute of Moscow during more than 30 years.
Когда я работал в министерстве, у нас был научно-методический совет по математике, который отслеживал уровень, объемы часов, даже содержание преподавания математики, подчеркиваю, не только на математических дисциплинах, но и по всем инженерным специальностям и по всем, и экономическим включая, там, где была нужна математика. Был такой совет, и возглавлял его Лев Дмитриевич Кудрявцев.
During the work of Professor Filipov as the Minister of Education of Russia, a special methodical council worked at the ministry, and this council was headed by academician Kudryavtsev.
Подчеркиваю, сейчас такого координирующего органа нет. Поэтому нам надо как-то обсудить и подумать, кто мог бы проводить нашу идею здесь, нужные идеи, доходить до нужных решений. И в частности, потом, конечно, можно вот через Андрея Андреевича Шкаликова выходить на Виктора Антоновича Садовничева, который сам математик, который занимается преподаванием математики и в школе организует эту работу. И, конечно, у Виктора Антоновича Садовничева есть рычаги воздействия на образовательные структуры, чтобы мы не потеряли уровень математики. Но нужны конкретные предложения, что в каком формате сделать, с тем, чтобы нам дальше отслеживать хороший уровень математики и в инженерных науках, и по нашим профильным направлениям подготовки: математика, прикладная математика, информационные технологии.
Nowadays we have no such a council, and something should be instead, but particular proposals are needed.
И знает хорошо Сергей Петрович, что наши математики все равно востребованы, работа математиков действительно интересна. Как бы мы ни говорили там про актуальность новизну, я всех призываю, здесь вижу молодые лица, молодежь, призываю, и больше будет выступать, еще больше, чтобы они послушали этих великих математиков, потому что это действительно может построить ваше хорошее будущее.
In spite of all problems, our mathematicians are needed worldwide, and our president calls all young participants to listen lectures, and this will be very important and useful for their mathematical future.
Причем ваши работы могут найти совершенно неожиданно, знает Виктор Иванович Буленков, может быть, это мою такую личную историю, когда я в 35 лет защищал диссертацию докторской в Стекловке. Это в моем издательстве в РУДНе, локальном, нашли мою книгу «Вариационные принципы для дифференциальных операторов», и американцы переиздали ее в Американском математическом обществе. Я даже об этом особо и не знал. Точнее, договор я заключал, но как они ее нашли, как они решили ее публиковать, я до сих пор этого не знаю.
Results might be very unexpected. For example, an old book of Professor Filipov issued in Russian were found by American Mathematical Society many years later, and published in English.
К чему это говорю? Что тогда это принесло большие доходы. Помните, долларами не давали, но чеками отдали большие деньги.
Это я не буду переводить.
Это не переводимый, что такое чеки, березки. Да? Я просто молодежь настраиваю, молодежь должна это понять. Я желаю нам с вами успехов, и очень хочу еще раз поблагодарить и Дмитрия Валерьевича Трещева, и передать через Андрея Андреевича Виктору Антоновичу, конечно, поблагодарить Александру Леонидовичу Скубачевскому за этот уровень, и особенно поблагодарить Сергея Петровича, что он, вот его даже участие у нас здесь говорит о том, что он думает, радеет за то, что наша советская российская школа, в которую он так много вложил, и которая в мире известна благодаря его имени, конечно, она должна развиваться, и нам надо послушать и его мнение, идеи, соображения, что нам надо делать для того, чтобы сохранить нашу российскую, советскую, хорошую математическую школу. И я желаю вам всем успехов, и должен буду идти, и вечером мы в 6 часов увидимся. Хорошо? Спасибо всем.
Our president thanks again Professor Treschev, Professor Sadovnichiy, Professor Skubachevsky, and especially Professor Novikov. And wish all of us a successful conference, and he will leave us for a while, but meet us again at about 6 o'clock.
Я хочу добавить, вы просто имейте в виду, что перевод был очень творческий.
Dear colleagues, a few words concerning our conference will tell us Sergei Petrovich Novikov. Please.
Я не знаю, как надо говорить, по-русски или по-английски.
На ваше усмотрение, Сергей
Вы
Петрович.
переводите,
Захотите
да?
по-русски, я переведу.
По-русски,
Захотите
хорошо.
по-английски.
Спасибо. Я очень благодарен организаторам, которые пригласили меня посетить и выступить участие в этой конференции. Надо сказать, что это замечательное место, в которое я бывал неоднократно в предыдущие годы, как вы видели из списков фотографий докладчиков в разных конференциях. Очень-очень мне это место нравится. И я желаю процветания этой школы, все-таки того, чтобы... И надо сказать, что здесь подходящее руководство и будущее, мне кажется, этим университетом.
This is a very good place. I was a speaker here many times. I am thankful for the organizers. I think that you have a great future.
Я хочу пожелать всего наилучшего участникам конференции и уверен, что эта конференция будет успешной.
I wish all the best to all the participants, and I am sure that the conference will be successful.
Dear colleagues, a few words to us will tell co-chairman of our organizing committee, director of Steklov Mathematical Institute, academician Treschev. Пожалуйста.
Dear colleagues, dear friends, I'm happy to participate in this meeting. It is very important in Russian mathematical and international, I believe, mathematical life. I estimate very highly efforts by Alexander Skubachevsky and his team concerning preparation of this event. In these days, some new problems appeared, and in fact, I believe that mathematics and other sciences should be kept as far as possible from politics. But in this world, there are people with another opinion, so problems appear. And anyway, I hope that this meeting will be very useful and very interesting for all participants. Okay.
Thank you very much, Dmitry Valeryevich. Next, a few words concerning this event will tell us Professor Eron, who is our speaker here online, unfortunately. Now, Professor Veron, please switch on your microphone.
You hear me?
Yes, we hear.
Okay. You see me?
Wait a moment, we shall see. Yes. We can see you.
Okay, you can see me and you can hear me. That's good.
Yes, please.
Okay, so dear colleagues and friends, it's a great honor and a pleasure and a responsibility for me to be there today to take part in this conference. Okay. The country I have been visiting a recurrent visitor to the country since 1974. So I think I've traveled a lot in USSR and in Russia, from St. Petersburg to Irkutsk and Akademgorod during this time. And it gave me the occasion to meet very great glories of the Russian mathematics, in particular in Moscow. And I have a special thought to respect to Stanislav Porozhev, who was a very good friend and an outstanding mathematician. Unfortunately for me, I'm not very good in learning foreign language, and I've never been able to speak Russian. And it's a big pity, because I like the culture very much. Now, for the conference themselves, I think I took part, as Professor Skubashevsky recalled it, in the meeting, the first meeting, the second meeting in 1999. And probably since I took part also in Petrovsky meeting organized by Professor Olejnik before, so I think we have met at that time. Okay, I remember that the situation was a bit different, and the first meeting of this DFDE were organized at the Institute of Aviation. Okay, well, today, unfortunately, I couldn't come because there are no more flights between Paris and Moscow, and this is an obstacle, and I deeply regret it. And I hope that the next meeting will be in normal situation, and that all the people will meet directly. And my hope also is that the scientific cooperation between Russian and Western countries' researchers will not be altered by the political problem between their government, and that new projects will continue to hatch, to develop, and to bloom in the future. It's extremely important, both for the science with a big S, and also for the young colleagues we need this type of action. So I hope this conference will be a wonderful moment. This is my talk. Okay.
Thank you, Professor Veron. Dear colleagues, now we start with our lectures. Chairman of this session will be Professor Taimanov. Iskandar Asановich, he is here. Yes, I can see him from the beginning. Please, Iskandar Asановich.
Ok. Bon. Nous avons fait un bon discours à la mode soviétique.
Okay, dear colleagues, it's my pleasure to introduce the first speaker, Professor Novikov, who will speak on nonlinear waves and solitons. Please, Sergey Petrovich.
About my scientific career. I started scientific activity as a student in 1950s. And there was a great development at that time in part of mathematics, which is called algebraic topology. At that time, it was like central part of big part of mathematics. This area was created by great scientist and natural philosopher Henri Poincaré, and but some preliminary ideas were also known earlier by Euler, Gauss, Riemann, Treschev, Maxwell, Kelvin, and finally Poincaré created this area. Let me observe telephonic. What is topology? What is it? Suppose you have geometrical structures. Or maybe what does it mean doesn't matter. At least some sort of metric measurements should be presented. I can deform such objects. The deformation is quite natural procedure. But what is important agreement leading to topology is that there should be no breaks in this, I would say, no разрывов, no shocks in this formation. What kind of properties are invariant under this broad family of continuous deformations without shocks? It's called topology. It's algebraic topology. Algebraic because there are many kinds of topologies. Topology of analytical, topology geometrical, topology combinatorial, even topology associated with even quantum field theory. So it is, by definition, this science may accompany several different areas of mathematics and theoretical physics, mechanics, and so on. In 1950s, scientific context recovered because since late 30s, this was our country was completely closed for foreigners, at least for scientists. Even translation of journals was closed in the 30s. For example, famous works of Kolmogorov was completely some Kolmogorov work was completely unknown in Western community. Its English translation was organized only in the early 50s. My late father also, his famous work was unknown. My friend told me when I worked in the United States, told me that some woman historian of mathematics told and said about famous work of Tikhonov, about this work of your father. So please make order out of that business. And I did that. In 1961, a group of famous topologists, which names are written here, Milner, Setzebruch, Dave, Cartan, Atiyah, visited Russia, and they helped me to reach international level. In our country, topology was, I would say, very good until 1950, but there was a 10 years long break. At that time, there was break between physicists and mathematicians in our academy. Let me tell you that it was not good for us, for mathematicians, because in mathematical leadership were amoral phenomenon several times, and it was not good work without to stay in academy without teachers. That's strange, but morality of thesis was much better at that time. That is very interesting for us. I was successful at that time. Solved one of main problems of topology, and some mathematical chiefs supported me and foreigners. I was awarded by Lenin Prize, accepted corresponding member of Academy, but soon everything changed, and since 1970, in our mathematics was period as, how to say in French language, night of San Bartolomeo. Yes, was like that was all 1970s. Mathematics was night of San Bartolomeo. In 1970s, my biography changed, and with my friend Yasha and I, we shifted from mathematical institution of theoretical thinking. There was a reason I was awarded by Fields Medal at that time, International Mathematical Union, but permitted for me. So, I started later shifted to United States. 25 years I worked in the United States. In 1992, I retired from the United States 5 years ago. And 4 months I spent in Russia. It's interesting. Mathematics is not simple. Amoral phenomena, amoral phenomena. And in our mathematics, but something else appeared. And the group of influential mathematics tried to replace me by some mathematician, average, very average level mathematician, who, however, disproved all history of human. And maybe you heard about whom I'm speaking. So maybe mathematics generates unknown. I heard in topology, and however, let me mention simply that topology, great topology as science of 20th century, started to decay. At the end of this great development, two famous problems were solved in topology, and I did not work at that time. Let me remind you that in 1980s, computational person jointly with topologists solved 200 years old four-color problem. And 100 years old Poincare problem was solved analytically. In 1960s, there were conversations, a lot of conversations in the community of theoretical physicists that such new sciences appeared, topology, and good to some new about something recognize. What is it? One good theoretical physicist, whose name is Shapiro, decided to learn topology. It was recommended by him some book written by two good topologists, my friends, whose name I will not tell you, by a reason which you will understand in a minute. This book was written absolutely formal, so formal that it was completely impossible to understand it. It was typical for mathematical literature of that time, why theoretical physicists did not like it. This was, I would say, record of such abstractness. So I will not tell names of this my friends, by clear reason. And Shapiro tried to learn this book, to read this book. He was unhappy, said that modern mathematicians are completely unreasonable people, tried to read Poincare personally, and of course, could not learn anything still. It was so many changes since that. When I worked in Landau Institute, I organized some courses, thesis. In our institute, thesis learned it. In our community, no, nobody could help them. This is my introduction. Sinai and I started new life in Landau Institute in early 70s, 1970s. And there was a number of remarkable theoretical physicists, whose name I will not list here. Some my students or former students also worked in Landau Institute. Their name is written, I will not repeat. Let me tell you that for contact with theoretical physics, it is part of mathematics, but different. The sense it is great mathematics, modern theoretical physics, created in 20th century. And my role, I learned theoretical physics 10 years. And I have two roles. My role was divided by two parts. One part, I helped them to enter in the new mathematical areas. Another one was I tried to help me to pose mathematical problems from materials, fresh materials appeared in theoretical physics, which required new mathematics. My first work, you may say that it is dynamical systems. I started to work from Einsteinian gravity theory. Physicists asked me about to help in that area. But some famous physicists, I used dynamical systems, complicated dynamical systems with my student, Bogorevlensky. And physicists obtained beautiful results, but very dirty, and nobody believed them, and institute asked us to verify it. This verification was okay. Finally, our method confirmed their calculations, but unfortunately, they found a regime of collapsing universe. Beautiful regime. We confirmed it. But physicists were not ready to dynamical systems. In early stage of universe, it is like dynamical system in open phase space. And in that case especially, statistics of properties of dynamical systems strongly depends on direction. We found, except confirmation of collapsing results, that for opposite time expansion of universe, it did not realize, could not be realized. Regular regimes appeared. Some famous hydrogen physicist, Yakov Borisovich Zeldovich, told me that at that time he was also astrophysicist. He told me that astrophysicists did not and were not able to read your work next 20 or 30 years. So let us give you problems in hydrodynamics and S. And I left this area, and my pupil wrote nice work in that area. But еще 20 минут. I changed area, started to work in linearization. Nonlinear solitons became my next area. It's beautiful mathematical discoveries made in 1960s, called inverse scattering transform method, was very popular at that time, and I started to work in this area. I worked here with my best students, long period, Brovin, Treschev, some hours. we effectively applied algebraic geometry, for example, non-standard area, calculating this in this nonlinear wave theory. In case of nonlinear waves and solitons, situation is such that, you see, it is well known in classical mathematics since time of Abel and Jacobi that completely integrable systems of dynamical systems, selected mechanics, there are completely integrable cases. First of them were found by Abel and Jacobi. And immediately algebraic geometry appears, integrating completely integrable system. If there is not, if group theory is missing, group theory leads to so-called trivial integrability. So it's necessary that algebraic geometry appears. If you have no obvious symmetry, there is algebraic geometry in that case. Last of them was famous case of Kovalevska. A lot of cases were found during 100 years of development. In this case, for Korteweg-de Vries partial differential equation, famous equation, it is famous because such sort of inverse scattering transform method was discovered for it. Instead of hidden symmetry, like in our cases, it was quantum mechanics appears. It replaces hidden symmetry of many completely integral cases. First of all, it was discovered for rapidly decreasing potentials, but after our work, with my best pupils, we solved periodic problems, and in that case also algebraic geometry appears full color. Let us come now to topology. Even in ancient world, people observed topological phenomena. Indian, how do you say, sophists, told to Alexander the Great problems how to discover knots. At that time, knots exist. Also, schema, knots. What did Alexander the Great? Alexander the Great took sword and cut off all these knots. Let me tell you that theory of knots is very complicated area of topology, but unfortunately, no applications is found until now. But my friend in biophysics made huge computational experiment to this. People, they were located in Kurchatov Institute. But nothing was here. Topology, algebraic topology is complicated area. It is not necessarily algebraic topology. Let us see combinatorial topology, continuous topology, differential topology, algebraic topology, topology and quantum field theory. Topology has a number of phases because it interacts with different areas of mathematics. Genius physics Dirac, being already old, relatively old, put following problem. Is there exists anything like magnetic charge? In magnetic configurations, always which we know on the Earth, which we know on the Earth, magnetic charge is zero. Dirac gave argument that it can be non-zero, but always integral number. Integral characteristics are typical for topology, necessary integral quantities. Topological quantities which I know for fiber bundles, including Pantregin and Chern classes, have always integer valued integrals over the cycle. Always. That's the nature of topology. Some partial case of that appeared out exactly in Dirac's considerations. I made analysis of that some famous cases make this analysis more or less simultaneously, but I found natural multidimensional generalization of that type of interactions. Very soon it was discovered in real physics, particles, and integrality here has interpretation like topological, like integrality of Chern class. Later, this became popular. My friends in theoretical physics, their opinion about such type of physical interactions, have different opinion. My friend Polyakov, now in America, famous physicist, that this is very good. My friend Fadeev in Moscow told us that is something completely uninteresting. So this point of view. But later this subject was blown up, and all my physical friends supported me in the international conferences, because that's normally, if something rediscovers what you did, frequently they try to ignore. My friend Albert Schwartz made some important discoveries, topological discoveries in quantum field theory, but then it started to be popular. Now let me come to my topological phenomena in normal method. So it is some crystal with psi 1 and strength means 10 to -8. System electroneutral. Neutral. So yes, there is a dual lattice, and in dual lattice, coordinates have dimension of momentum. In original lattice, it has dimension of length, and quantity, length multiplied by momentum divided by Planck constant should be integer number. It is number. So there is a lattice here, one-dimensional on this picture, and there is a first. If in quantum theory, lattice is, how do you say, factorized by lattice. So instead of lattice, line, we have circle. Exactly what is going on in angle on the plane. But in multidimensional case, in theory of normal metals, lattice is three-dimensional. So we have three-dimensional torus. But lattice. Elementary lattice, brilliant section. Standard set is just minimal lattice, minimal part of lattice. What is going on for zero temperature in Kelvin? Situation is very simple. Electrons are Fermi particles. It means that two electrons cannot occupy the same place in spectral theory. So therefore, starting from lower level, electrons are higher and higher for absolutely zero temperature. Let me ask you how it is. I may tell you about 100,000 Kelvin. But nobody is fitted. It is some structure. It is something structured. That there is some properties. Lattice may have two invariants, rank and genus. Genus, yes, lattice. Electrons, by Fermi statistics, electrons a lot of electrons, and final surface is so-called Fermi surface. It is located in three-dimensional torus of quasi-momentum. That's that terminology from physics. So mathematically we have torus, three-dimensional torus, and function, level of function, which is called Fermi surface. Let me just last example, genus and rank. Now we come to our business, to dynamical systems. Suppose I have magnetic field, very strong magnetic field. Piotr Leonidovich Kapitsa was champion of strong magnetic fields and low temperature. Maybe low for him was 1 Kelvin at that time. Now it is, say, 10 to minus 3 Kelvin, very normal low temperature. A magnetic field, 1 Gauss is approximately magnetic field of Earth. So 10 to 4 Gauss is 1 Tesla. It was, but today they can do about 70 Tesla. It is strong magnetic field. And if I have magnetic field in my torus with Fermi surface in it, its plane orthogonal to magnetic field covered surface. And I have dynamical system on the surface. Dynamical system. Complicated development. At that time when this idea appeared, physicists did not know dynamical systems at all. The subject was many theoretical physicists told me later. We return to that problem. Supported by literacy of both books even elementary topology. So this is a Fermi surface. That's interesting. Gold, platinum, and so on. They have complicated Fermi surface. Complicated means that it will be surface of genus. Some methods have trivial round. This is time to pay our attention. There are 2 types of critical forms. First of all, trivial orbit. Second, all orbit. Not all orbit. Cases which was established. Several miles. Finally, we found something What is interesting is that if you return to that picture, the picture from left, it leads to trivial asymptotics. I will not tell you what kind in electrical conductivity we have in both the cases. Other cases in directions of magnetic field is two-dimensional sphere. It is two-dimensional manifold. And what such type regimes occupy full measure, even more. Complementary domain is third dimension, no more than one. Probably less than one, but it was not proved. It's some difficulty. Numerical experiment shows that less than one, but can't prove it yet. What is interesting is following. When you have such open trajectory, we established that it is torus. It is not here. It is torus. Now our discovery was that it is always integer direction. Integer. In torus, you have a countable number of integer directions. It is so in that picture. I think it was our main discovery. That there are mathematical models complicated pictures. And as end word, let me tell you my friend, theoretical physicist, told me in Israel, he very competent guy. He probably you are right. But after that he had great smile and said, but experimental physics already passed that. So you have to develop this in mathematics. That's not in physics. Because nobody will give you money for that. That's not. Nobody will give you money for that. Anyway, let me finish my talk with a remark. Physical mathematical science there was a great development of these sciences in 20th century. Physics and mathematics. Physics is born, ladder, mathematics is computer, and such great development. Theoretical mathematics. Nobody knows if the development successful now or it is diminished. But in our time, just concluding remark, in our times, different areas of even of mathematics started to go out of like galactic and universe were go the opposite direction and don't understand it. should understand reality, that different areas of mathematics need algebra and topology if they don't understand each other. Some leaders in big math community should exist who understand, but most people will not. But reality. My friend, big friend, Gelson, he always learned different areas of mathematics. Others did not want to learn. They wanted to learn only if they want. But it is very important. And I always follow this example. You have to learn other areas. Maybe you will find that also home for future work. Maybe not opposite. How do you find home for future work if you don't know this area? You cannot find. So I hope that we are people. Right? We are not galaxies. Maybe we have to work in order to keep different areas of mathematics understandable, all of us. Thank you very much.
Let us thank speaker. Are there any questions, comments? Okay, we're slightly out of time. Let's thank the speaker again. There is a proposal. We shall make a break for 10 minutes, and there will be no break between two next talks. So we're starting just 1 minute after 13. because we have to start soon our next talk. Okay, dear colleagues, let us start our next talk. The speaker is Professor Dmitry Treschev from Steklov Mathematical Institute, and the title of his talk, Linearization by means of potential. Please.
Usually in my talks, I try to concentrate on the main result, but since the main result may look a bit too special, I will try to spend more time on motivations, open questions, and the series of problems I am interested in concerning this domain. So. Just a moment. Great. So I consider Hamiltonian system of this form. You see, and in fact, I am interested in a local problem near the origin, which is the equilibrium position, and it is totally elliptic equilibrium position, for example, but not in this example, but not necessary. So you see that here we have in linear approximation, so which corresponds to quadratic part of the Hamiltonian. We have several independent harmonic oscillators with some frequencies omega j, which will be non-resonant. And also we have some higher order perturbation, so we study this very classical problem. What we know, the theory of normal forms says that in some canonical coordinates, our Hamiltonian some new coordinates x and y capital, the system can be reduced to the following form. So again, the part H naught, so harmonic oscillators, but then we can kill most of terms in Taylor expansion of our perturbation, and we can reduce the perturbation essentially to this term, which depends only on these combinations of variables, xy square plus y1 square, and plus similar terms for other indices. And this can be made up to some reminder of arbitrary power. So you see power n here, and it would be better to have index n capital here also for this function n, which is polynomial of the corresponding degree. And so This is standard. This is the theory of normal forms, and we can ask if we take n and make it increasing to increase and to tend to infinity. What we will obtain, and it is known, and these results go back to Ziegel, that in general we should expect divergence of both of this, but this some details are more modern. So we should expect the divergence of this function of the series f, and the divergence of the change of variables. So when n tends to infinity, and my question is a little bit not very standard, not very classical. So suppose that my function, my Hamiltonian function, depends on some functional parameter, and so this parameter is this function phi. It is important that in my question, this function depends on some not so big number of variables. So you see that the total number of variables in my system is 2n, n vector x and the vector with n components y. But the standard case is when my parameter depends on only n variables, not 2n. And the question is it possible to obtain to find this the value of these functional parameters, to find this function phi, so that the system is linearizable. That this means that in some canonical coordinates the function is this one, h naught of x y again. So just a combination of harmonic oscillators and nothing else. So why such question appears? The origin is from my study of billiard. So billiard systems. So I remind you that billiard system is dynamical system of the following kind. We have some flat domain and the particle inside, and inside the domain particle goes along straight lines, and reflection is elastic reflection. So these two angles coincide. The incidence angles and the angle of reflection are the same, and we can associate with this dynamical system some map of a two-dimensional cylinder to itself. Why cylinder? Because take a point on this curve sigma 1 and the angle theta 1. So this data determines uniquely the orbit, the trajectory of the billiard, and then if we go along this trajectory, then we meet another collision point sigma 2 with another angle theta 2, and this map theta, sigma 1 theta 1 to sigma 2 theta 2 is the name of this map is billiard map. It was introduced by Birgov, and he discovered, he noticed that this map preserves area, some special area on this cylinder. Why cylinder? Because sigma 1 is on a point of a circle, because this is a closed curve, and theta 1 is a point on some interval between 0 and pi. And so this is the definition of billiard system. It preserves area. This means that it is a kind of Hamiltonian system with discrete time. And the question I asked about 8 years or 9 years ago is as follows. So consider this billiard curve, which determines the system, symmetric in two perpendicular axes, x and y. And in fact, you see that I consider some local billiard dynamics near this orbit of period 2. If we have the interval on y-axis is corresponds to the orbit of period 2, and my question and I am interested in the local dynamics near this orbit, and in this case the billiard curve is determined by graphs of two functions, f and minus f, and this function f is even due to symmetry of this of my domain, and so this is the Taylor expansion. The Taylor coefficients are A0, A2, and A4, and some normalization, trivial normalization may be with this one. So A0 is minus 1. And so in linear approximation, we obtain some linear system, so either rotation or some hyperbolic rotation. And my question is it possible to choose the billiard curve so that the billiard map is locally a rotation on the plane, so but rotation in some special in some coordinates. So in dynamical systems, people say the map is locally conjugated to the rotation of a plane by some angle, so you see that this question 2 is very analogous to the question 1 from the first slide. So we just replace the Hamiltonian system by this special Hamiltonian system with discrete time by the billiard map, and just the functional parameter here is this function which determines the curve, the billiard curve. And we have several versions of this question. First version is formal version. Is it possible to construct the Taylor series for this function? And if this is the case, then we can ask about the radius of convergence of this series. If this radius is 0, or this means that the series is just formal, or the radius of convergence is positive. We can replace the case of rotation by the case of hyperbolic rotation, and we can discuss also the case higher dimensional version of this billiard system. Suppose we have some billiard in some three-dimensional space. So we have some head downstairs, had some surface upstairs, and a periodic trajectory of period 2, and so the same local question about the possibility to linearize our system. I more or less, when I started to think about this problem, in fact, there are some motivations for this question. I will have to skip them. When I started to think about this problem, I understood that more or less that if we have non-resonant situation, this means that the angle of rotation is incommensurable, rationally incommensurable with 2 pi. This means that this number is irrational. Then formally, the question has positive answer, and this is more or less this is not a profound result, because we just have to construct an equation for this function f. I do not present this equation here, but it exists, and then we should see that from this equation, one by one coefficients of the series f can be constructed. And what was very unexpected for me, that for good rotation numbers, this alpha divided by 2 pi, the function has positive radius of convergence. And I discovered this numerically, and this result remains to be just numerical. So this is not a theorem. This is just conjecture. And this was very unexpected for me, because I mentioned the standard situation in the theory of normal forms when we expect the divergence of all these procedures, normalization procedures. Moreover, again, I present here some other numerical results. This graph shows us dependence of the radius of convergence, dependence on alpha. Alpha is on this axis, on horizontal axis, and on vertical axis we have the radius of convergence of the corresponding series. And we see here a graph of some smooth functions, and this would be quite usual thing, if not one fact that this function is not defined at any rational point, because we have resonances. Alpha divided by 2 pi should be irrational. So this graph is dependent. This function is defined only on some some complicated Cantorian set. And in fact, functions of this kind, which look as smooth functions, but on some set with a lot of holes, are discussed in literature, and they are called Whitney smooth functions. And so, and my another conjecture is that the function which is essentially associates with alpha the radius of convergence of that series for the function f is Whitney smooth. But again, this is just conjecture based on numerical computations. And I would mention that this numerical evidence of convergence of the series for the function f are based on examining of many coefficients of the function f. These coefficients a naught and a2 and a4, and they not just grow not very strongly. They in fact they have some asymptotic behavior, and so they remind something like a geometric series multiplied by some polynomial prefactor, and so this there is some structure in this coefficient, in the behavior of this coefficient. Okay, now I turn to the very first question on the very first slide, and I turn to when I tried to prove these conjectures, conjecture 1 or conjecture 2, I was not able to do anything. And my next idea was to include this problem into some class of problems, which part of which maybe will look simpler, and having this experience with simpler problems, maybe it will be possible to return to the original problem. I turn to the very first question 1, concerning Hamiltonian systems, but in the simplest possible situation of 1 degree of freedom. In this, here I slightly changed the notation, and so we see here just one harmonic oscillator as the first part of my Hamiltonian function, and some perturbation, which depends, you see, which depends on some parameter phi, a functional parameter, and this function phi in this case should depend only on one argument. So I repeat the question. I would like to find this parameter in such a way that the system is linearizable, so it can be reduced in some coordinates just to the Hamiltonian function can be reduced to the quadratic part of my Hamiltonian function. And so in fact, in this case, if in some coordinates the Hamiltonian function is just quadratic, this means that the system is isochronous. This means that all solutions of my system is all solutions are periodic solutions, and the period doesn't depend on the solution. And in fact, there is some literature and some history on the problem of isochronicity of isochronous systems, and the situation, this domain starts from Huygens, who discovered that cycloidal pendulum is isochronous. This means that if you have some well which is determined by cycloid and in the gravity field, and the point oscillates in this well, then the period of oscillations doesn't depend on amplitude or on energy. And then many authors tried to study this kind of problems. They constructed many many examples of isochronous systems, and I should mention here Abel works, classical works of Abel, and more modern works by Piskunov, Urabe, Stillinger, Dorignac, and many others. And probably the main the best result in this domain belongs to Gorny and Zampieri, who presented constructed description of all isochronous potentials. And in fact, almost all people studied the system when this function h phi is just function phi or which depends only on x. In this system, we can in this case we can regard y squared divided by 2 as the kinetic energy of our system, and x squared divided by 2 plus this phi of x as a potential. And in fact, almost all results consider this situation. And in this situation, you see h phi is just phi of x. Gorny and Zampieri presented very nice, very clear constructive description of all isochronous potentials phi of x. And now I turn to the results which deal with Hamiltonians of more general form. And I studied with my students several examples. And the first idea was just you see this perturbation should first to spoil isochronicity, spoil linearity of my system, and then by using this phi function, we want to recover this isochronicity. And so you see that in this example 2 means that we spoil isochronicity by this terms of order 4, and this function phi, it is quite natural to look for this functional parameter in this form, the function phi, which depends on x squared plus y squared, because I remind you that exactly this combination is presented in the theory of normal forms. And the result is as follows: that if the series, this series for the function phi can be computed, that the formal solution of the problem, the formal answer to the question is positive, but these coefficients phi j grow like factorials. In fact, this is not a theorem, because it was more or less convincing for me to see this growth looking at several first coefficients phi j, but maybe I will find some time to prove this rigorously. In fact, this means this example means that even in the case of 1 degree of freedom, we can obtain a divergence in some problems of this kind. I remind you that in billiard we had always convergence. So my students Yelfimov and Cherkasov studied the following case when our Hamiltonian was a product of a function of x and function of y, even functions, and the sum of functions phi of x and phi of y, again even functions. And in this case we obtained some positive answer to the question, but not only a formal positive answer, but positive radius of convergence for the function phi. So again, the results were these two results are very similar. So we take arbitrary function f with some normalization, natural normalization. For example, f of 0 is 1 in this case, and f prime is 1 here, and some other natural conditions here for values and derivative at 0, but only just two Taylor coefficients. So f is arbitrary modulo this normalization, and the phi is taken with similar normalization, but then we want to this function to make our system isochronous, and the result is that phi can be always constructed. And then the radius, if f is real analytic, then phi is also real analytic. So I turn to my main result. It is in fact a generalization of this example 4. So I take arbitrary perturbation. My perturbation is arbitrary, but just even in both in x and y, and this function phi enters as some additive term, again even, and so the theorem is as follows: that for any real analytic H star, this perturbation, there exists this function phi, which depends only on one variable, which makes the system locally isochronous, and moreover, we can prescribe dependence of the period of a solution on the energy, and this is another real analytic function t. And so we take we can take arbitrary function t, and then we obtain that the function phi also again exists, and real analytic such function which makes the system to have this dependence of the period on time. The idea of the proof is we use the fact that the system can be reduced to quadratures, and by using some changes of variables, changes of functions, we can reduce the problem to the solving of such an integral equation, where u is unknown function, is a function of one variable, but in this function we should substitute square root of the energy multiplied by sine of some angle alpha, but we in fact you see we integrate in this alpha, and the function psi is known, is given, and we want to construct this to find this function u, and to prove that it is real analytic. And to find this function is a series. To find the series, Taylor series for this function is again not so difficult. We just looking at this equation, we see that Taylor coefficients for this function u can be obtained one by one, just equating terms of this series. In fact, this equation can be regarded as equation for series in H. This square root disappears because u prime is even function and u square here is also even function. So no square roots appear in the equation. And after that, we have to prove convergence of this series. And here I use measurand methods. But in fact, again, this needs some work, some technique to prove this. So I will not comment on this. And certainly we can ask what happens if this perturbation is not even. So this is some open question for me. And again, for me it is some mysterious problem why this additive why this functional parameter phi of x square gives us convergence of Taylor series for phi. But if we put here x square plus y square as an argument, we obtain divergence. What happens? What is the mechanism which distinguish convergence and divergence? And also we have some questions in higher. Now we can turn to multidimensional situation. What happens if we have maybe 1.5 degrees of freedom, maybe 2 degrees of freedom? What happens in this situation? And now I just start the numerical study of this case. And first evidence shows some divergence, but probably some this numerical these programs should be tested if they compute correctly everything. And do I have some time? About 7 minutes. Maybe I just mentioned here another result in this direction. In fact, if we just a moment, if we study the problem of isochronicity, so we have this harmonic oscillator plus higher order perturbation, then it turns out that we can obtain just constructive criterion for isochronicity in terms of Taylor coefficients of this function H star. I just mentioned the result and show you how it looks like. So first we turn to it is convenient to turn to complex variables. Not instead of x and y, we deal with z and z bar. This is standard. This goes back to Birkhoff and maybe even to Poincaré. And then the harmonic oscillator will have this Hamiltonian z bar, and here we have Taylor expansion for the perturbation, where mu is just mu to the power beta is a short notation for z to the beta 1, z bar to the beta 2, and so beta is two-dimensional integer vector. And you see here that the summation starts from the terms of order 3 and more. And so we first to present the result, it is all the result is presented on this slide totally. So first we should consider some special sums. All this over Taylor coefficients, and all these sums are finite. And you see that the sum sigma kd depends on two integer indices, and k is just the number of multipliers in each term, and d is presented here because here is the conditions of the summation. So beta are indices Taylor for Taylor coefficients, and the main condition is this one: that the sum of these degrees but these two-dimensional vectors should be take this resonant value d plus k, this two-dimensional vector, and in terms of these sums, we obtain just infinite number of polynomial conditions which are equivalent to the condition of isochronicity, and then maybe okay, but it seems to me that it is time to stop here. Thank you for your attention.
Okay, let us thank the speaker. Are there any questions, comments? Probably we have time for one brief comment. But started with your idea to prove the existence of some non-trivial integrable billiard, yes? How it is the situation with it? Do you believe that it will finally get to your example?
Yes, in fact, results numerical results in billiard looks for me very unexpected and very nice, and so certainly I tried to imagine some other similar problems, but at the moment I didn't see any problem of some physical nature or some geometric nature, but you see that the general setup is just general Hamiltonian system. But even there, I do not know when I should expect convergence, on when I should expect divergence. So this is the main question here.
Okay, if there are no more questions and comments, let us thank the speaker. And we have to announce the third talk just now, and it would be online, yes? How that would be done?
Yeah. It's a good question.
Is Professor Veron ready?
I am ready, but the question is...
Okay, then now speaker Professor Veron, who will speak about the singular problems for mixed quasilinear equations.
Okay, but how to transfer my okay. Just I have to see how can I open the good How can I? We have some difficulty to see how can I share the screen. It worked theoretically last time.
What's the problem? Please share your screen.
Yes, I try to do it. I say I want to share my screen, but the question is, how can I open the? I don't see how to open the what I have on my desk.
Ah.
This is when
to share the screen from organizers.
I have it on my desk, but I don't know where to put it.
For sharing the screen, he has to be permitted to do that.
Yeah, and yes, but I have given the authorization. The question is how to do. I have the file is on my screen, and well, yesterday it worked finally, but I don't know now today how to open it. Yeah, you don't see my screen. That's the problem.
Thank you for your attention. That's written on your screen. We're seeing this picture.
On my screen, I see. I try to see how I can open, but I have not. Camera is open. Okay, I think you will listen, but I think the sharing screen is open, but I don't know what to put. Where to put my where to put the file?
Just open the file on your screen. Just
okay.
All the screen has to be filled by your PDF file or your presentation, and then just share the screen.
Okay.
There is okay. We are seeing.
What do you see?
Have to maximize it because you see, we see your screen.
You see. Okay. Now I'm going to force. Okay, full screen is okay. What do you see now?
Okay. We see it now. Yes.
Oof.
Okay. Please.
Thank you. Thank you very much. I'm sorry. I'm not at all good in computer science. You know, for me, it's very, very complicated. Okay, so I would like to speak of a problem that it's about the boundary singular solution for a class of mixed quasilinear equation, and it's a joint work with Marie-Françoise Bidot-Véron and Marta Garcia-Huidobro from Santiago, and it has already appeared in CVPDE. The starting problem is the following. You take omega to be a bounded domain, C2 domain. P is bigger than a parameter which is bigger than 1. And Q is a parameter which is between 1 and 2. And M is a number, a positive number. And the question is to study the boundary behavior of positive solution of this equation LPQM of U. Okay, what is it? This is minus Laplacian of U plus UP minus M grad UQ equals 0. So what is the interest of this equation? Okay, you have a diffusion coefficient, the diffusion operator. You have an absorption term, and you have a reaction term, which is here, which is a gradient U to the Q. There is a competition between those two terms. There is a competition, and they are not of the same nature. Okay, well, similar problem, I will speak of it later on, has been a study in the whole space, but today I'm emphasizing on the boundary behavior. Okay, I'm going to follow two directions: existence of solution with boundary measured data, and description of the solution with a boundary isolated singularity. There are exponents, critical exponents in both in P and Q, and there exist also critical values for M. Okay, just now a specific connection between P and Q is Q is 2P over P plus 1. In that case, the equation 1, my first equation, is invariant under a change of scale. I call it TL, which is defined by TL of U is L to the 2 over P minus 1 U of Lx. Okay, when we analyze this configuration now, when Q is less than this 2P over P plus 1, in some sense, the absorption term is dominant, and the behavior of singular solution is modeled by the Emden-Fowler equation minus Laplacian of U plus U to the P is 0. When Q is bigger than 2P over P plus 1, the source term is dominant, and the behavior of singular solution is modeled by the aconal type equation, UP minus M gradu Q. The diffusion plays no real role in that case. And finally, another equation which plays a very important role is the Riccati equation, which is minus Laplacian of U minus M gradu to the Q is 0. So you see the behavior of solution of my first equation is modeled by these three types of equation. And of course, what is important is the role of the parameter. And now in the critical Q, the case Q equal 2P over P plus 1, the equation is invariant. Then the value of M becomes fundamental. Okay? And we will use also very much the solution of the Emden-Fowler equation minus Laplacian of U plus UP is 0, because it's a subsolution of the equation, while the solution of the Riccati equation minus Laplacian of U minus M gradu to the Q is 0 plays the role of a super solution for this equation. Now, okay, if we want to analyze boundary value problems, I have a space of test function, which is called x of omega, which is the space of function in C1 of omega bar vanishing on the boundary with Laplacian in L infinity. Now, if we want to define a weak solution, okay, this is formal green formula. And if I have this formal green formula, we go to say, just to say something that what is related operators with singularities and measure boundary value. Okay, when M is bigger than 1, okay, we have the equation minus Laplacian plus UP plus M gradu Q is 0. In that case, we have two absorption terms. So this has been studied by Marcus and Nguyen. Now the equation with two source terms, that means minus Laplacian of U minus UP minus M gradu Q is 0. So we have studied this with Villeveron and Marta Garcia Huidobro. Okay. And finally, when you reverse the role of UP and M gradu Q, that means you minus Laplacian of U minus UP plus M gradu Q. This is, in that case now, it's no longer an Emden-Fowler equation which plays some role, but it is a Lane-Emden equation. And in that case, this has been studied by Villeveron and myself. Okay. Now, what does that mean now? The first problem is to understand problem with isolated boundary, with isolated singularity on the boundary. So what is this problem? You assume that P is, so my first theorem is the following. I assume that P is bigger or equal to n plus 1 over n minus 1. So this is a critical threshold for the boundary value problem for the equation of Emden-Fowler. Okay. Now I assume that P is bigger, M is positive, and you assume that you have a solution which is C2 in omega and C1 in the closure of omega minus 1 point. The equation is satisfied in the interior, and U vanish on the boundary except 1 point. So that means in some sense that the solution may develop a singularity on the boundary. And you assume also that the solution is positive or non-negative. Okay, the result is the following. Then if U is, okay, the good space for studying this type of problem is the result for studying this type of problem, then you know that in that case, your initial solution belongs to L1 of omega. UP belongs to L rho to omega. Rho is the distance to the boundary, okay? And grad U belongs to LQ rho, and rho always being the distance boundary, okay? And in that case, the equation is satisfying in the following sense, that the integral over omega of minus U Laplacian zeta plus UP minus M grad UQ zeta is 0 for all function in the space of test function. And this is now under what condition? Under what conditions this is true? Okay, remember that P is just bigger or equal to n plus 1 or n minus 1, and M is positive. So condition is either P is n plus 1 over n minus 1, and Q is subcritical. That means respect to the critical threshold. That means Q is less than n plus 1 over n. Or P is bigger than n plus 1 over n minus 1, and Q is less or equal to 2P over P plus 1. Okay, this is a condition in which you have a removable singularity. And furthermore, if we assume that the assumption I, that means P is n plus 1 over n minus 1, and Q is between 1 and n plus 1 over n minus 1, then, or if we assume that P is, I'm sorry, I'm going to continue. Either we assume I, that I recall, or we assume that P is bigger than n plus 1 over n minus 1, and Q is subcritical respect to P. Or P is bigger to n plus 1 over n minus 1, and Q is critical respect to P. And in that case, M is smaller than some specific value, which is called M star, then U is 0. So this is the system is a bit complicated, but we have to recall that for the simple Embden-Fowler equation, the threshold for removable singularity is P is n plus 1 over n minus 1. Okay. And now for the other equation, that means the other equation minus Laplacian equal grad U to the Q, then it is superharmonic. So in some sense, it can develop singularities naturally. Okay. So this is the first result. Okay. I notice two things. In the case I, that means P is n plus 1 over n minus 1, and Q is less than n plus 1 over n, then it's not said, we do not say that the solution is identically 0. Okay? In that case, there may exist solution with a blow-up on the boundary, but this blow-up is not detected in the sense of distribution. That means the equation that I gave before with the test function is satisfied, but there is a singularity, but at the energy level. This is something which is known for equation of Lennenden equation, either minus Laplacian of U equal U, for minus Laplacian of U equal U to the P. For boundary singularity, this was studied by Vido-Véron and Pons and myself. And for the internal singularity, it was studied by Caffarel, par Guidas and Spruck. Okay, so this is so these are not singularity. These are singularity, but not real singularity in the sense of distribution, only at the singularity in the sense of energy. Okay, what is the technique? The idea is first to obtain an a priori estimate. The a priori estimate is not so complicated for this type of equation, thanks to the absorption term. The a priori estimate is the following. If M is positive, and Q is less than the minimum of P and 2. And if the equation is satisfied, that means the equation is satisfied 1, 9. I'm going to recall what is 1, 9. This is the equation. A solution which satisfies the equation in omega and which vanish everywhere on the boundary except one point. So in that case, you have this estimate. U of x is bounded by the maximum of m to the 1 over p minus q, x to the minus q over p minus q. And so this is an agonal type equation, and x of minus 2 over p minus 1. This is the Emden-Fuller type estimate. Now, after you have that, since q is less than mean of p and 2, you can have a gradient estimate, which essentially is obtained by differentiation of this exponent here. That Laplacian of u of x is bounded by C2 max of x to the minus p over p minus q and x minus p plus 1 over p minus 1. How to obtain this? The technique is linked to this type of, I call it this Osserman type estimate. First, you make a change of variable. You say that u is v to the b, and the b is between 0 and 1. And you look at the equation which is satisfied by v. So you have this equation, minus Laplacian of v plus minus b minus 1 grad v square over v plus 1 over b times this one minus m times, okay, this coefficient here times v to this power and times. So when we analyze this, if b is less than 1, okay, this is in some sense, it's a good term. And this is a good term. This is an absorption term. So it's the question is how to deal with the bad term. The bad term is this one, if we want to apply just a kind of maximum principle. So we want to control the bad term, and we do it by Hölder inequality. And in the Hölder inequality, we write like this, okay? We have this estimate. And what we get minus Laplacian of v plus 1 minus b minus m times this coefficient here, grad v square over v. So this has to be positive if we want to have plus 1 over b v to the p plus 1 minus b minus 1 minus this remaining term. Now this term is, so the gradient term has disappeared in this. And now I have two powers. So what I want, if I want to use techniques from a Osserman type estimate method, I want this coefficient here to dominate this one. Or if they are equal, I want these terms not to be too big compared to 1 over b. Okay, the exponent of v, you can compute it directly. Under what condition this coefficient here, 2b minus 1 q minus 2b minus 1 divided by 2 minus q, is smaller or equal to p minus 1b plus 1. So this is equivalent, and this is independent of b, and this is equivalent to q less or equal to 2p over p plus 1. Okay, so this will be very important for the a priori estimate. Now, I choose b to be equal to this value, and then I have obtained, in that case, p minus 1b plus 1 is n plus 1 over n minus 1. This is called the removability threshold for a boundary singularity of Emden-Fuller equation. Okay, now in the case p bigger than n plus 1 over n minus 1, q is less than 2p over p minus 1, we have a wonderful choice, which is epsilon to this value here. And now the equation is just minus Laplacian of v plus this coefficient here, which is a positive 1, v to the n plus 1 over n minus 1, less or equal to some constant a. But this is a result from that I proved with Gmira 33 years ago, that the solution is bounded. And then after that, you have all the regularity. Now, in the case p is bigger than n plus 1 over n minus 1, but q is 2p over p plus 1, you make the same choice of the value of b, but I remember that I told you, you have to make a sharper choice of epsilon compared to m. Okay, And the last case is P is n plus 1 over n minus 1 and Q is less than n plus 1 over n. So this is a critical threshold for the equation minus Laplacian of U plus grad UQ is 0. Okay. So in that case, we use the equation, the estimate on the gradient. This is for 1, 3, 1, 4. And then we use a bootstrap argument and derive the boundedness of U. So this, it may look complicated, but actually it is not so complicated compared to the estimate, which is when you want to have estimate for singular solution of minus Laplacian of U equal U to the P. In that case, you are obliged to use the Bernstein method and the differentiation of the equation. Here it is essentially, it is just no differentiation of the equation, essentially Osserman type method. Now, okay, so we have the removability of points. Well, it's natural to say if you want to remove something which is bigger than a point, so how do you do it? In that case, you have a rather technical result, which is the following. Then if P is bigger than n plus 1 over n minus 1, and you assume that you have a parameter R between P and n plus 1 over n minus 1. So if one of the two following conditions is satisfied, either Q is 2P over P plus 1. So in that case, remember that the value of M is fundamental. Then and M is smaller than this specific value, M double star of R, which is this one, okay? Or if if Q is less than 2P over P plus 1 and R is less than 3, but M is arbitrary, then you can remove a set which has a 0 C2 over R prime capacity. That means if you have a solution of this equation here, which vanish on the boundary except on the set K, then it is identically 0. Okay, in the case, I just recall that in the case of Emden-Fowler equation, this is a result by that we prove with Marcus. Then in that case, you can take R equal P. And the result we have with Marcus is that if you have a set for the equation minus Laplacian U plus UP is 0, and which a solution would vanish on the boundary except on the set K. If the C2 over P, P prime capacity of K is 0, then the solution is identically 0. So the case corresponds. Okay. So this is this case. Now, if we want to solve problem with measure, okay. So how do we define a solution, a weak solution with measure? So we define the solution, a weak solution is measure, okay, formally by using the green formula and a function which vanishes on the boundary. So what I have integral over omega minus U Laplacian of zeta plus UP minus 1 U minus M grad UQ and this zeta, and this is equal to minus integral over d omega of d zeta over dn dmu. So this is what happens if the solutions are regular with a boundary which is regular. Now, if this is going to be my definition of weak solution. This will be the definition of the weak solution. But in order to give a meaning to this, remember that the function zeta vanishes on the boundary. So zeta is bounded by c times rho, the distance of the boundary. So I want to give a meaning to this, up minus 1 u zeta. So I want u to be in LP rho. And the same here, I want grad uq in LQ rho. This is important for giving a meaning to this formula. To this problem, I am going to associate two problems with measured data. And then Fowler equation minus Laplacian of V plus Vp minus 1 V is 0, and V is mu on the boundary. And the Riccati equation minus Laplacian of W minus M grad W to the Q is 0, and W is mu on the boundary. Okay, I associate to this problem, and those problem has been fairly understood. Okay, and for the problem 122, that means then Fowler equation with measured data, So with Marcus, we proved that we have a solution if and only if the measure is absolutely continuous with respect to this Bessel capacity C2 over PP prime. This is a capacity in dimension n-1. So you compute it by local chart, and this is a standard Bessel capacity. So this is absolutely continuity of this spec. Remember that, for example, if P is bigger or equal to n plus 1, if P is smaller than n plus 1 over n minus 1, so only the empty set has zero capacity. Okay, that means that we can prove, we can solve when P is less than n plus 1 over n minus 1, and we can solve the problem with any radon measure on the boundary. This is an old result that I proved with Gmira in 1989. Now for the problem for the Riccati equation. We proved with Hoang and Nguyen that if the measure satisfies this, there exists a solution to this problem, to this problem 123, if the measure is Lipschitz continuous with respect to the capacity. So you see it's different here. It is just like continuity, and here it's Lipschitz continuity, that there exists some constant C, such that for any E in d omega, the absolute value of mu of E is less than C times the C2, the capacity, but now the capacity corresponding to Riccati equation is 2 minus C, 2 minus Q over Q, Q prime. Okay? And now I can state the main result concerning if I want to solve the problem with a complete equation. Then I assume that if P is bigger than 1 and Q is between 1 and 2, and mu is a non-negative measure, radon measure, which satisfies mu of E is bounded by C times the minimum of the capacity C d omega C 2 minus Q prime of E, and capacity C 2 over P prime of E. So it's not this is valid for all Borel sets for some constant C. Then there exists a positive number C0, such that if little c is smaller than C0, we can solve the problem 121 with one boundary data C mu. I remember that 121 is this 120 or 121 is this one. That means but you have to replace mu by C mu with C less or equal to C0. But you can solve the problem. In particular, if P is less than n plus 1 over n minus 1, then there exists no condition on P. And if Q is less than n plus 1 over n, then there exists no condition on involving this capacity here. You see that in some sense it can be reduced. Now what is the proof? The proof is in some sense a rather funny proof, because we are looking for positive solution. And what is important is that if I take any solution, okay, if I take any solution of this equation, any positive solution of this equation, then I remember that this equation is a subsolution of this equation. For positive solution, it is subsolution of this one. And this one is a super solution. So the question, if there exists a solution u mu of my problem, in that case, it satisfies this. Okay, so I want to compute it. I want to compute this, and now if I have a solution v mu and a solution w mu, I know this is equation which is satisfied in omega. So I know that this is a subsolution, this is a super solution. I know that in between those two solutions, there exists a solution of the same equation. Of course, there is I don't know anything about the boundary behavior, but I'm going to use this is called the sandwich principle. The sandwich principle is the following: that I know that I am using the sandwich principle is based upon the trace, existence of a boundary trace. That I know that the limit when delta goes to 0 of the integral for the on the set rho is delta of W mu zeta ds. This is integral of a d omega of zeta d mu. This is for any z in C of omega bar. And this is also for the, and then Fowler equation, this is the same result. We have also the, if there is a solution, we have the same boundary trace. So in between, we have the same, we have the same necessary, we have the integral of the rho of x is delta of u mu zeta z ds is equal to integral of z d mu. So at the sense of trace, this equation that we have constructed here, it satisfies this equation. It satisfies the equation with a boundary trace which is mu. Now we have to check about the, if I want to have the a solution in the sense of, if I want to have solution in my weak sense, of course I need now to say about the integrability condition. I need the integrability condition. And what estimate I have? The solution of the Emden-Fowler equation is smaller than the Poisson potential of the measure mu. Okay, and the solution of the Riccati equation with measure mu is bounded from below by the Poisson potential of the measure mu. Remember that everything is positive. But now we can prove also, this is proved that W mu is also smaller than C times the Poisson potential of mu. Okay. So what do we have finally? We have that integral of V mu. We have that sorry, not integral. We have that V mu is positive, is bounded by U mu, what we are interested in, is bounded from above by W mu, and is bounded by C Poisson potential of mu. Now, remember that I have my assumption, the assumption for solving V mu is absolutely continuity of the measure respect to the capacity. But if the measure is continuous, is Lipschitz continuous respect to the capacity, I have also an existence result. I have the existence result, and which says that the following: if mu of E is bounded by C times the C 2 over Q prime capacity of E for some C, then there exists a solution Z between, there exists a solution of the equation with, this is the Lane-Emden equation. I use it only in order to have an estimate. I use this equation, but it is, so this is the use of the Lane-Emden equation. Now, of course, is satisfied Z is bigger or equal to the Poisson potential of mu, then this implies what? The Poisson, Z to the P is in L1 rho. Then this implies that the P of mu is in L, that W mu is in LP rho. Okay, but if WP is in LP rho, this implies from here that U mu, because of this, is in LP rho. Okay, so the use of the function Z here is just to have an estimate of the Poisson potential of the measure in LP rho. It was not that I didn't have it before. Okay. Now for it, well, only term which is missing now is a gradient. For the gradient, what I do, I just write phi is a g of omega of u mu, the mesh solution to the P. Okay. This is in L1 rho, so I can, this has a meaning. And what I have minus Laplacian of u mu plus phi is grad u to the mu to the q. So this is a u mu plus phi is a positive superharmonic function. This implies that this term here is in L1. This, by Doob's theorem, this implies that this term is in L1 rho. So I have finished now. I have obtained that grad u mu is in LQ rho, and this is This is what I was looking for. Okay, so you see it's rather strange because it uses equation, the Lane-Lamdan equation at some moment in order to solve the problem, and it's a bit unexpected. But the principle, in some sense, the equation is satisfied inside. Then we have the sandwich principle and the trace, and from the trace we can give the estimate. Now, okay, in the book of Adams-Hedberg, there are many results according, in particular, when a capacity is dominated by another capacity, and the coefficients are complicated. But I just say that in some sense, for example, if P is bigger or equal to n plus 1 over n minus 1, and Q is between 2P over P plus 1 and 2, then the only capacity which is important is C2 minus Q prime capacity. Okay, that means the other is dominated, so we have no problem with that. The same now if Q is between n plus 1 over n and 2P over P plus 1, then the only capacity which is important here is C2 over P prime capacity, always using the Adams-Hedberg type of result. Okay, so this actually, that means we can solve in the full range of PQ is 1 infinite times 1, 2. We can prove that this is a consequence of those two corollaries, that only one capacity actually is involved for solving the problem. The other is controlled by the first one. Okay, now I'm just going now to say a few words about, if I want now to study precisely the boundary singularity, it is natural to look, I'm going to look at it in the case Q equal 2P over P plus 1. In that case, I'm looking for separable solution. That means solution which are of the form R to some power times omega of S. S is a spherical variable. So this is because we have an invariant by scaling, and invariant by scaling is equivalent to the fact that we have a self-similar form. In that case, if U is a solution of L, PQ mu is 0, and which it in omega and vanishing on the boundary. So I look at what happens if for a solution under this form. In that case, we see that omega will satisfy minus delta prime of omega plus alpha times n minus 2 minus alpha times omega plus omega p minus 1 omega minus m times alpha square omega square plus grad prime omega square to the p over p plus 1. Delta prime is a Laplace-Beltrami operator. Okay, this is a Laplace-Beltrami operator, and this is maybe abstractly it can be in any domain of the sphere. That means the cone generated. Now, if S is the full sphere, then the positive solution of this equation are unique and constant, thanks to this term. These are the terms. Just maximum principle. This is very easy. So in that case, the problem is completely solved. Now, in the case of if I want to study boundary singularities, the natural model case is S is Sn minus 1 plus. That means half sphere. In that case, this model case, I have the problem which I want to solve the equation for that means equation L Pm of omega is 0 and a solution. This is on the upper hemisphere, Sn minus 1 plus, and omega vanish on the equator. Okay, something which is that I prove with the Gmira. There exists no positive solution in the case where m is 0 and p bigger to n plus 1 over n minus 1. Okay. Now, I have this following result. Then there exists, okay, also with Gmira, we prove that if p is less than n plus 1 over n minus 1 and always m is 0, there exists positive solution, very easy to obtain by minimization. Okay, now if the I look at the full problem with M non-zero, then I have one positive solution, either if P is between 1 and n plus 1 over n minus 1 and M is positive, or and M is positive or 0, okay? Or P is n plus 1 over n minus 1 and M is positive. Remember that with the mirror, result with mirror, here with M is 0, there exists no positive solution in this case. Now, but with M is positive, even for this critical threshold, there exists a positive solution. Okay, and now in the case where P is less between 1 and 3, or P is bigger than n plus 1 over n minus 1, and M is large enough for some specific, then there exists also a positive solution. You see that the situation is a bit complicated, and the constriction is made by use of super solution and sub-solution. Sub-solution are under this form, and the super solution is a bit more complicated, but it uses also this transformation. So I will not go too much in the details. And now for the boundary behavior, I have the following, that if you have, now in the subcritical case, that means P is between n plus 1 and n minus 1, and Q is less than n plus 1 over n. We know that in this range, there exists a solution with Dirac mass boundary on the solution, on the boundary. So actually, then for any K positive, there exists a minimal fundamental solution. That means a solution on the boundary which behaves like the Poisson, the Poisson kernel at this point. Okay, and actually, those solutions satisfy this equation LPQM of 0 and in omega with boundary data, which is just a Dirac K times a Dirac mass. Okay, now what happens when K goes to infinity? UK is increasing. UK is increasing, and what you say, well, we know that there is a because of the a priori estimate, there is a limit of UK when K goes to infinity. So it's something which blows up on the boundary, but it exists. Then this limit is infinite. Now what we know about this limit U infinity has two possibilities. Either the we associate, okay, in order to I want to associate the spherical, the special separable solution of the Emden-Fowler equation. That means like M equals 0. Okay, this plays some role because in some sense, for some blow-up, the Emden-Fowler equation is dominant. Okay, and I have the following result, that if P is between n plus 1 over n minus 1 and Q is less than n plus 1 over n and M is positive, okay, I have either Q is less than 2P over P plus 1. In that case, limit of R to the 2 over P minus 1 U infinity of R is a function psi, and psi is a unique positive solution of this equation here. Now, if Q is equal to 2P over P plus 1, in that case, we have the full equation. Then what we know, it's less precise, but we know that R to the 2 over P plus P minus 1 U infinity of R behaves like omega when R goes to 0, and omega is just the minimal solution of the full equation, 133. What is yeah, this is my full equation here. This is equal to 0. Okay, now in some other case, it's more complicated because we have if Q is dominant with respect to 2P over P plus 1, then the blow-up is modeled by the aconal equation. As the aconal equation, in that case, there is a blow-up rate which is Q over P minus Q. The difficulty, of course, is that the solution of the aconal equation are, in some sense, in Rn, are isotropic. That means are invariant by rotation, which, of course, is not the case of a solution would vanish on the boundary, except one point. But we have this type of estimate for a solution which goes in the case where the aconal equation is dominant. Okay, this is this case. Okay, just to say now something about problems, extension problems, because I think my time is going to finish. If I want to, there is some solution which are modeled by the Riccati equation. Remember, the Riccati equation is minus Laplacian of u minus m grad uq. So the equation in that case, the coefficient, the blow-up coefficient is 2 minus q over q minus 1. So in the radial case, in Rn, you have specific solution which have this form. There exists. We do not have up to now the equivalent of this type of blow-up for solution with boundary singularity. We believe that it exists, they exist, but we don't know how to prove it. Okay, there is another problem, which is the boundary trace. The boundary trace, also something interesting is to understand the equation dtu minus Laplacian of u plus up minus m grad uq. You have all the possibility of variation on this problem. And one problem is interesting is to say what kind of initial boundary, initial value can be accepted for this equation, and or if you want, what could be the initial trace of positive solution of this equation. Okay. And just saying a small something about the other equation. That means I reverse the sign here. I make an equation. Now this is the model. This is a Lane-Emden equation, which is much more complicated in sometimes than the Emden-Fowler equation because we do not have Osserman estimate. And I have now but I have here the forcing an absorption term. Okay, so this is a paper which that I've done with Overon. What we prove essentially, we have a priori estimate. A priori estimate, well, in that case, this is a Lane-Emden type equation. So the a priori estimate is limited by the value p is n plus 2 or n minus 2. This is a completely different techniques. The technique is essentially, well, the one which has been used by Kittner, Souple, and Polacek, and by called of doubling lemma. And also, if I want the equation here to be dominant, if I want the Lane-Emden to be dominant, I have to take q is less than 2p over p plus 1, less or equal. Now, if it is equal to 2p over p plus 1, in that case, I need an estimate on m. But this type of result has already been obtained. Okay, with boundary measure, it's very simple because there is always a trace. There is always a trace for minus Laplacian of u minus up is 0, or the trace for minus Laplacian of u plus m grad uq is 0, boundary trace. So this is the same sandwich principle and the same capacitary estimate. And now the boundary trace, in some sense, is easier to obtain. Well, the boundary trace is when there is the bad term usually in the boundary trace is absorption, when it, in particular, when it is a case of Emden-Fowler equation, because it can give existence of boundary measure, which are not Radon measure, but Borel measure, which are infinite Cern compact set on the boundary. But in that case, this term here is in some sense superharmonic. So boundary trace of superharmonic function is fairly understood since the work of Doob. And in some sense, the boundary trace of this equation is understood. Okay, this is what I wanted to say. And okay, thank you for your attention and see you soon, I hope. I chose this painting because I like it very much. It's a painting by Levitan. It is in Treschev, I think.
Sorry, example of what?
This painting, I say. I put this painting because I like it. It is, I think it is in Treschev.
Yeah. Treschev Gallery, yes.
Of course, it's in Treschev.
Are there any questions or comments? Let us thank the speaker again for his fabulous talk and recalling us this picture.
You know him. I hope that you know this painting, no?
No, probably.
Oh,
No, not.
you have a wonderful museum in Moscow.
Okay, there's conjecture that it's painted by Levitan, but it's
Levitan, yes.
reminded us about this possibility to go to Treschev Gallery and see this.
Oh, yeah.
That's a good idea. Okay, thank you very much. And now we're finishing our morning session. Thank you,
Okay.
Fatih.
Okay, so
Fatih.
bye.
Напоминаю. Итак, следующий доклад. Значит, следующее заседание у нас в 15:20 здесь же. Обеденный перерыв, извините, сокращен. Но это, видимо, только на сегодня. Ну, наши